Section 13.3 Physics and the Quantum Mechanic Model. Light and the Atomic Spectrum. Section 1 Light and the Atomic Spectrum. The quantum mechanic model of the atom grew out of the study of light. According to the wave model, light consists of electromagnetic waves. Electromagnetic radiation includes radio waves, microwaves, exemplified by the pictures, infrared and light, infrared and visible light, ultraviolet waves, X-rays, and gamma rays. Parts of the wave: wavelength, amplitude, origin, crest, trough. Parts of the wave explained. The origin is the baseline of energy. Crest, it's the high point on a wave. Trough, low point on a wave. Amplitude, distance from origin to crest. Wavelength, distance from crest to crest. Wavelength is abbreviated by the Greek letter lambda. Light and the atomic spectrum. Waves travel at 3.0 times 10 to the 8th meters per second in a vacuum. That would be in space. Amplitude is the wave's height. From here to here, or from here to here, from origin to crest, or from origin to trough. Wavelength is the distance between crests. You can use the troughs, or you can use the amplitudes for the crests. Light in the atomic spectrum. Frequency is the number of wave cycles to pass a given point per unit of time. Frequency and wavelength are inversely related. As wavelength goes up, frequency goes down. As wavelength goes down, frequency would go up. And this doesn't refer to the physically going up or down, it means the length of the wavelength. Speed of light. We use the symbol c. Wavelength is, speed of light is wavelength times frequency. unit of frequency is the hertz, which equals cycles per second. How many wave cycles will go through a certain point in a given amount of time. A prism separates sunlight into a spectrum of colors. As you can see in the picture, we have white light going in and causing the light to be split into its spectrum of colors. Red has the longest wavelength but the lowest frequency. Violet has the shortest wavelength and the highest frequency. So we get more wavelengths through a given point with violet because it's short. Red, we get fewer wave cycles through a given point at a given time. Light in the atomic spectrum. When a gaseous or vaporized element is excited by electricity, only a few lines are emitted. This would be the atomic spectra for each of the elements that are electrified. Here we have two examples. We have nitrogen, and this is nitrogen's atomic spectra. You can see all the different wavelengths of light that make it through. And we have mercury's atomic spectra. So this is mercury going through a vaporized and the light being shown. But here on the top is the spectra that you would see. You see 1, 2, 3, 4 major lines of coloration. That is the signature for mercury. White light should be a continuous spectrum of the emitted or all the colors. Every element will emit light when it is excited by the passage of electric discharge through its gas or vapor. Here's an example of sodium. The atomic emission spectrum is produced by passing the light emitted by an element through a prism. The few lines of light produced is called the light spectrum. So here again is the neon. Here again is the mercury at the top. This is the light as the electricity goes through the gas. Quite similar to that of a neon light. The emission spectrum is unique to that element. Helps to identify an element.